do not necessarily agree with putting comparators in the same chapter as jump and MCR. We're going to concentrate our efforts on comparators, and we'll talk about jump and MCR, but it's not going to be something that you guys need to really concern yourselves with. Okay, hopefully by the time we get done today, we use a compare instruction to energize coil. You guys know what compare instructions are? I want to take a wild stab.
Comparing two things?
Comparing two things, exactly. Are they equal? Are they not equal? One greater than the other, and so on, right? Program compare instructions in series set up upper and lower limits in a control system. Use limit test instructions set upper and lower boundaries in a control system. Those two are basically the same thing. The way the limit instruction works, and we'll get more into it later, is you set a low limit and a high limit. As long as the value that you're testing is between those two limits, then the instruction will evaluate as true and allow the logic to continue. The second bullet point is talking about instructions and compare instructions in series. You have a greater than in series with a less than, and they're both testing the same thing. It does the same thing as a limit instruction does. Use jump and label instructions, skip over rungs in PLC ladder logic diagram. I have been doing this for better than 30 years, and I have never come across a program where somebody actually used jump label or MCR. Not even once. They serve the purpose. They do act differently, so you need to know what to expect whenever you use them. The chances of you actually running into one in the wild is pretty slim, in my opinion. Use multiple jump label instructions in PLC ladder diagram. Use compare instructions to energize jump. Use master control to halt the operation of a section of PLC ladder logic diagram. So those are your compare instructions. Equal, A has to be equal to B. Not equal, A cannot be equal to B. Less than, A is less than B, greater than, A is greater than B. Less than or equal to, A is less than or equal to B. Greater than or equal, A is greater than or equal to B. So, always, always source A and source B. And then, what relationship do you want to test for between them? When PLC is scanning ladder diagram, sometimes one or more rungs should not be scanned. When a rung is not scanned, state of the instructions on the rung remain the same. Conditions for skipping over rungs can be generated either by state of an input, contact, or as a result of a compare instruction. That's the jump label we're talking about there. In the lab, it talks about you have a tall bottle or object, whatever it is, and a short one. And the short one doesn't need to have a couple of the operations done on it. So if you detect a tall bottle, you do everything. If you detect a short bottle, You do the first one, skip the next couple of them, and do the rest, I mean, whatever that looks like. In reality, you could make the argument that that would be the best way to write the logic, to skip over what you didn't need. But what are the chances that you're going to have two different products rolling down the same line that you need to do operations to in the real world? Pretty slim. Okay. Equal. We're going to blow through these because they're basically all identical other than the condition you're testing. Okay. In every comparator instruction, source A must be a register. So N7, F8, so on. Okay. Source B can either be another register or just a number. So you're always testing to see if source A is equal to 13 or whatever number you pick. Then you can put 13 on source B and it works just fine. You cannot say is 13 equal to some register though, because it doesn't like that. Source A always has to be a register. In this particular case, 0 is equal to 0, so that will evaluate as true, starting on your pilot light. Okay. Not equal, source A must be register, source B can be register or number. In that case, 0 is equal to 0, so that will evaluate as false, turn the pilot light off. Less than, A must be register, B register or number. 0 is not less than 0, it evaluates false, turn the light off. Greater than, A must be register, B must be register or number. It can be register or number. 0 is not greater than 0, so the pilot light's off. Less than or equal to, source A must be register, source B register or number. 0 is in fact less than or equal to, because it's equal to 0, so pilot light's on. Greater than or equal to, A must be register, B can be register or number. 0 is in fact greater than or equal to 0 because it is equal, pilot light's on. I told you they were all pretty much identical. Limit test. You set upper and lower boundaries in the control system. The test source must be a register. Upper and lower limits can be a register or a number. Okay. The way that limit looks, believe it or not, that's a rectangle. I have to straighten that out. I ain't gonna have room for writing. Have source A, test, and source B. Okay. So whatever I'm testing, say, cumulative value of counter C50. Okay. I want that to be between, say, 13 and 15. As long as that evaluates as true, because source A would be either 13, 14, or 15. Okay. All three of those here that would evaluate as true. So this is basically greater than or equal to, and this is less than or equal to. Okay. Or I can look something like that. That way, if I need to change the value of source A and or source B, all I gotta do is change the values in the register. If you hard code these as actual numbers, then you need to make a change. You have to go in, edit the program, re-download, all that crap. If you make these registers, those can be edited on the fly while you're online. And you set it whatever you want. Okay, so here's the kicker. What if, say N70 is 13 and N71 is 15? What does C50 cumulative value have to be in order for that to evaluate as true? 13, 14, or 15. Exactly. No difference than whenever I had the hard-coded numbers in there. But what if that's the case?
It's false.
Good guess. And my response to that is sometimes. You know, if source A is greater than source B, then you're testing for everything except what's between there. So anything from, it's the 16-bit controller, anything from negative 32,768 all the way to positive 32,767, except if it was 13 or 15, it still evaluates as false. Okay, mask equal. We're not going to worry about mask equal. You guys remember how masking works? You mask it with a 1. It's evaluated. If you mask it with a 0, it's not. Remember this? I was looking at me like, what are you talking about? And this is what I'm testing. And that's my mask. One and 0 is 0. 0 and 1 is 0. 0 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0. 0 and 0 is 0. 1 and 0 is 0. 1 and 0 is 0. 0 and 1 is 0. 1 and 1 is 1. 1 and 1 is 1. 0 and 1 is 0. So if I mask this binary number with this mask, that's going to be my output. But all I got to do is say if test and mask are both one is true. Basic and truth table. Both A and B have to be one in order to get one out of them.
Remember that. That's hard.
So you can mask bits in your, whatever it is you're testing, because you don't care whether they're on or off. And then see if what you have left is equal to some other value. 30 plus years I've never used it, not even once. PLC ladder logic diagram using limit and mask equal. Kind of go commit it to your brain camera and move on with life. Jump. Unconditional jump. Always assigned a number. Must have a label instruction with the same assigned number. Associated label must have the same address. You can have up to 256 jumps and the pertaining label functions in a PLC ladder logic diagram used to formulate if, then, else programming. So if this is true, then we do this. If not, then we do that. Otherwise, we just go on with life. Okay. Thing about jump instruction. We have whatever that looks like. Okay. If whatever that is evaluates as true, it's going to jump from here to here, jump right over these. Okay. That means it does not process them at all. So if these are physical outputs, colon, whatever, if it was off when this evaluated is true and we jump past it, it'll stay off. If it was on when that evaluated is true and we jump past it, it's going to stay on no matter what the conditional logic for it says in the meantime. As long as you're jumping over it, it's not processed at all. There's nothing that says write to the output data table at those three addresses because we bypassed the logic, it's not even there. Okay. Conditional jump, that's actually what I drew there. Master control reset, MCR, works exactly the same way. Except they work in pairs. So, as long as this evaluates as true, MCR is on, it'll do everything in between. Okay. If that evaluates as false, MCR shuts off. Everything in between will also turn on. And it'll go here and continue on. That's the major difference between jump, label, and MCR. Anyway, jump, label, the conditional logic in front of the jump instruction has to evaluate as true for it to do the jump. It does not update any outputs, any output instructions while it's jumping. MCR, the conditional logic, has to evaluate as false for the master control to work, and any output instructions between the two MCR instructions will clear to zero. Must be energized to be activated. The jump instructions between jump and label will be skipped. Master control must be de-energized. Activate instructions between master control or instructions are all turned off. Logix Pro example, which you can't read anyway, we don't use Logix Pro, so.